Hi everyone, I'm glad to present our work enhancing atomic instruction emulation for cross-ISA dynamic binary translation. This is a joint work of Nankai University, University of Georgia, and University of Minnesota at Penn State. Cross-ISA DBT stands for Cross-Instruction Set Architecture Dynamic Binary Translator, which is a key enabling technology for cross-platform developing and testing, as well as some commercial code transitions such as Rosetta 2 in the up-to-date Apple MacBook M1, which is also a dynamic binary translator that supports x86 code to run on Apple's RISC processors. The key idea of cross-ISA dynamic binary translation is to provide equivalent code semantics for a different architecture. For example, a NOP instruction is first translated to intermediate representation code in dynamic binary translator. After some code optimization, the intermediate representation is then translated into host x86 instructions, where the semantic equivalence is guaranteed. However, in the state-of-the-art DBT, we found that atomic instructions are not practically emulated. For instance, when the guest ISA is RISC, such as ARM, its atomic instruction, low-link and store conditional, which we will talk about later, is translated into compare and swap semantics by dynamic binary translator. According to our observation, compare and swap do not provide equivalent semantic and the low-link and store conditional, which may cause the emulated instructions vulnerable to ABA problems. Here is an outline of this presentation. Besides our motivation, the background section would provide some details about RISC atomic instructions and how the wrong emulation would lead to ABA problem. Then in the design section, we'll introduce the challenges and then our solution to address those challenges. In the evaluation section, we compare our solution to the current existing best solution, and finally we conclude. In the RISC architectures, load link and store conditional are a pair of instructions used to achieve atomicity for many read-modify write instructions. Any memory access operation is monitored by the exclusive monitor. Load link sets an exclusive memory region, EMR, to mark an atomic variable and load the data to register. Then the store conditional first checks the EMR flag, and if the EMR is still valid, the SC succeeds. If not, it reports a failure and triggers a retry of the LLSC until it succeeds. During the load link and store conditional, any memory update operation from another core to the atomic variable will destroy the EMR's flag, causing the SC checking to fail and retry. This is how LLSC works as an atomic instruction, and it prevents ABA problems by nature. However, after the translation, the atomic checking is performed by compare and swap, which follows the idea of nothing is changed if the value is the same. In this example, the load link records the current variable's value and the old value. All the update operation will not be monitored during LLSC. The SC checks if the current value equals the old value, and if so, it infers that nobody has changed the value since LL. So the SC rarely succeeds, which leads to an ABA problem. ABA problem may cause double free or deadlock issues that lead to crashes or even return the program with wrong results. You can read our paper for more details about how ABA problems cause crashes. Our major design goal is to maintain the atomicity of LLSC. Here we define two levels of atomicity. The strong atomicity guarantees that any change to the atomic variable protected by LLSC from another thread will break the atomicity, causing an SC failure. In comparison, the weak atomicity only guarantees that only atomic instructions updating the atomic variables break the atomicity. Since atomic variables are rarely updated by non-atomic instructions, enforcing weak atomicity without monitoring normal store instructions could provide adequate results for standard programs with reduced overheads. There are mainly three previous solutions. The first solution is to implement a software exclusive monitor, which means there is extra memory checking before every store operation. As all the stores are instrumented, this could introduce huge overhead. Another solution is to let MMU, the memory management unit, to perform the checking, which means the exclusive memory region is protected as read-only, so any store to the exclusive memory region will trigger a page fault. This solution only intercepts stores to the read-only exclusive memory region and leave other stores free from instrumentation. There is also a hardware-based solution that uses hardware transactional memory to protect the LLSC region in order to achieve atomicity, which could be fast and correct but relies on additional hardware. But Are these conventional intuitions really true? No. According to our design and observation, with an efficient lock-free hash table, software checking scheme could be fast, correct, and portable. The seemingly promising page protection-based scheme, however, could result in large overhead due to page-level fault sharing and system call overhead. Also, the hardware transactional memory could be challenging to implement in dynamic binary translator. We here introduce the first solution, HST, which stands for hash table-based store test. The key idea is to instrument store to add additional memory checking before memory access. Therefore, the challenge of such solution is the store instrumentation overhead. We found that the store instructions account for up to 20% of total executed instructions, and they are highly concurrent in multi-threaded programs. We did a simple experiment by implementing stores with the standard exclusive monitor semantics, which first finds the EMR and uses a lock to achieve the atomicity of updating EMR metadata. The baseline is the execution time without store instrumentation, and we found that instrumenting stores in this way causes up to 45 instrumentation overhead in single thread execution, and causes over 100% overhead due to the locking synchronization. Therefore, the standard exclusive monitor semantic is too slow to be accepted by dynamic binary translator. Instead, our design has to be fast, which means we should only implement a lightweight checking procedure that only contains a few additional instructions. Our design also has to be scalable, which means we have to avoid locking. Toward this, we propose a lock-free hash table design. The guest memory space is mapped into one lock-free hash table, where every hash table entry represents an EMR region that corresponds to one or more guest memory addresses. The important part of the hash table is that every entry contains only one 4-byte integer that represents the EMR's owner's thread ID, TID. And we can use this only TID to implement LLSC semantics. There are two operations to the hash table. Hash table set writes the current thread's TID to the EMR TID, and a hash table check reads from the entry and compares the EMR TID with the current thread's TID. Since writing to a line 4 bytes is guaranteed to be atomic, these two operations are atomic by nature, and therefore they are thread safe without a lock. Based on the lock-free hash table, we can implement the ABA safe LLSC. The low link first performs a hash table set, then writes its TID X to the EMR TID field, and the store conditional performs a hash table check to check if the EMR TID still equals its TID X. After the load link, the EMR TID is set to X, and we suppose the atomic variable is A. If the store from thread Y to the atomic variable happens at this time, it will be instrumented to perform a hash table set first, and the EMR TID is set to Y, and then it writes to the atomic variable. If another store writes the atomic variable back to A, the store conditional would notice that EMR TID is changed, and infers another thread touched the atomic variable, so it fails. Another challenge is the race condition between SC and store. At a lower level, a store conditional first checks the thread ID, and if equal, it then executes a memory update operation. However, if a store happens between the checking and updating, even if it changes both the EMR TID and atomic variable, it would be too late for the store conditional to get noticed, resulting in a wrong SC success. Therefore, we have to guarantee the atomicity of SC. The first scheme, HST, stops all other threads execution and then performs the store conditional operation. After this, it resumes other threads execution. This scheme guarantees strong atomicity. However, since in most programs, atomic variables can only be modified by atomic instructions, we can only keep the atomicity between LLSCs. This is the idea of HST weak, which uses lock to avoid race condition between LLSC, and it guarantees weak atomicity. More details about the atomicity and correctness can be found in the paper. Solution B, PST, stands for Page Protection-Based Store Test. The key idea is to use memory management unit to automatically check stores, so no store instrumentation is needed. For example, a load link first protects the atomic variable as read-only and sets an EMR. Then, if another core wants to update the atomic variable, it triggers a page fault, and the EMR is then marked as invalid. In comparison, stores to other locations won't trigger any page fault and is free from instrumentation. To maintain the atomicity of SC, the PST scheme stops the word to prevent any risk condition, and PST remap uses the remap system call to remap a virtual page to another virtual address to get thread-level privilege separation. Details are in the paper. The third solution is based on hardware transactional memory. A conventional intuitive idea is to map the LLSC instruction to a transaction. That is, the load link starts a transaction and store conditional ends the transaction. In this way, all the instrumentation between LLSC are guaranteed to be atomic by HTM. But is this solution correct? Since load link and store conditional are frequently translated separately, there could be a code translation procedure happening between LLSC emulation. If so, the translation function becomes a part of the transaction, and its large memory footprint frequently exceeds the hardware transactional memory's transaction limit, causing a transaction to abort. If such a transaction aborts, the translated host code would also be rolled back and erased. Another problem is that SC could be jumped over, so no one calls the transaction end function to stop the transaction. To be specific, some LLSC contains a compare and jump semantic in the middle. It compares the load link value with 0, and if not 0, it calls a branch if not equal instruction to jump over the SC. So no one will call the HTMX function to end the transaction, and the transaction will last forever until it triggers an abort, and then it rolls back to the very beginning of load link. And it may repeat the same procedure again. These two problems could lead to frequent transaction aborts and sometimes live locks. To prevent these problems, our solution is to combine the HST scheme and HTMs together. So this is the HST scheme. The load link sets the hash table and SC checks the hash table entry and then update memory. Remember we talked about the SC racing condition. So here, we could use HTM to protect only the SC region to maintain the atomicity of SC. We instrument stores with hash table set, so the store between LLSC is checked by the lock-free hash table, and store and SC racing condition is avoided by the HTM protection. Combining these two, it is called the HST-HTM scheme, and it provides strong atomicity. By doing this, the transaction only covers the hash table check and memory update procedure, so it has a small footprint. Also, if the SC is jumped over, no transaction would begin, and the transaction end is guaranteed after the transaction begins. We here give a brief summary of mentioned designs. The HST scheme uses a lock-free hash table to check stores between LLSC and uses stopping the word solution to keep the strong atomicity of SC. The HST weak is based on assumption that all the atomic variables are only accessed by atomic instructions. So HST weak only enforces weak atomicity between different LLSC transactions. PST tries not to instrument every store by using memory management unit page privilege protection. Only stores to the protected read-only atomic variables are intercepted by page fault and others are free from instrumentation. The HST-HTM is a correct design of HTM in dynamic binary translator, which uses a transaction to protect the atomicity of SC based on HST. There are several questions to answer for the evaluation section. The first is to verify the conventional assumptions that long exist in the community. The current QEMU saves all value and checks on store. Is it fast but incorrect? The LLSC instruction support via MMU is implemented as PST. Is it fast because it avoids instrumenting all stores? For the link helpers and instrumented store solution, we propose HST and compare it with the current best existing scheme PicoST that implements the standard exclusive monitor semantics. Are there big performance impact by having a store instrumentation wrong for every store? Besides, are the solutions scalable in multi-threaded programs? If not, what is the performance bottleneck? And what is the best trade-off between correctness, speed, and portability? To evaluate the solutions, we run an ARM parallel programs in the Parsec benchmark suite on an x86 host machine through QEMU. We have two machines. Machine A has 52 CPU cores. To evaluate the HTM-based solution, we use machine B that has Intel TSX support with 10 CPU cores. To evaluate the correctness of the solutions, there are formula proofs in the paper. For experimental proof, we design an ARM lock-free stack that uses load-link and store conditional to avoid ABA problem. You can access the code in our repo. The program runs correctly on native ARM machine, but crashes on QEMU emulation. For the straightforward HTM implementation, it would fall into live lock. For all other solutions, the lock-free stack successfully executed. To measure the scalability, we run the parallel programs compiled to ARM on x86 QEMU from 1 to 64 threads. We first draw the scalability curve of the current QEMU, which is an incorrect solution, but we can use it as an upper bound. The x-axis is the number of threads increasing from left to right, and y-axis is the speed up normalized QEMU single-thread execution time. Then the PICO-ST is the best existing solution that implements the original exclusive monitor schematics, but we can see from the graph, its scalability is bad due to the lock and its instrumentation. Here we add the green line to represent the scalability of HST scheme. It performs better than PICO-ST, and for some lightweight synchronization workload, such as Black-Scholes and X264. HST could reach a good scalability. We'll analyze its overhead later. The HST weak scheme reaches nearly ideal scalability as the original QEMU. We can see that PST scheme has scalability concerns. Although there is no extra store instrumentation, frequently setting up the page table limits its scalability. For HTM-based solution, we compare HST HTM with HST scheme. They both guarantee strong atomicity. The difference between HST and HST HTM is that HST HTM do not need synchronization in the SC. We can see that without the synchronization in store conditional, HST HTM reaches nearly ideal scalability at the QEMU. Although there is a scalability dropping, the thread number exceeds the CPU core numbers. Here we only have 10 CPU cores, so too many threads would introduce more LLIC and therefore increase the HTM's burden. We here try to locate the bottleneck of each solution. The x-axis is the thread number and y-axis is the execution time. The first bar from the left is the time consumption of PICO-ST, and its overhead includes instrumentation overhead and synchronization overhead. The figure shows that the major overhead of PICO-ST is the store instrumentation overhead. The standard exclusive monitor instrumentation introduced 20% to 45% overhead, no matter how many threads or how many LLC instructions there is. For the HST solution, the store instrumentation overhead is reduced to less than 5%. However, since the store conditional introduces synchronization between threads, it could introduce large overhead when there are too many threads. The PST scheme wanted to reduce the store instrumentation overhead by utilizing page protections, but the blue bars show that the system call, like mprotect, becomes the new overhead. Therefore, the PST scheme did not succeed in reducing the instrumentation overhead due to the large system call overhead. Also, due to the page granularity protection, PST suffers fault sharing issue, which may cause frequent SC failures. Details can be found in our paper. Here, we compare the atomicity, speed, and portability between different solutions. According to our experiments, HST is believed to be fast and portable, while maintaining strong atomicity, which is 2 times faster than the best existing scheme. HST weak is also a portable solution that sacrifices strong atomicity in exchange for nearly negligible overhead and can provide adequate results for programs that correctly use atomic variables. The HST HTM solution relies on hardware transactional memory. The PST solution is found to be slow due to page-level fault sharing and large system call overhead. The PICO-ST is the baseline, which is incorrect and portable but slow. The QEMU currently uses an incorrect translation scheme, and the straightforward HTM solution is incorrect and may fall into live lock. In summary, the lock-free hash table-based scheme provides fast and correct design to protect LLSC free from ABA problem, which provide over 2 times speed up over the best existing scheme. Since the current bottleneck lies in the synchronization in SC, there is some potential techniques to reduce or replace the stop-the-world synchronization. An instruction called double compare single swap atomically compares two different separate variables and performs one store. However, such instruction is not currently available in commercial processors. This could be used in hash table check and memory update procedure to avoid SC racing conditions. Another solution is to provide thread-level privilege separation using the new hardware feature provided by Intel Memory Protection Key, which provide a thread local permission control. We can also consider changing the whole translation scheme, since the key drawback of dynamic binary translator intermediate code is that it does not provide LLSC semantics. So one potential solution could be directly map the high-level guessed LLSC semantics, like compare and swap, fetch and add, to host atomic semantics provided by host kernel and GCC. This is called the role-based code translation. Another solution is to add new IR semantics to provide correctness for LLSC. Our code is available at GitHub. For more interesting details such as how we handle the semantic difference provided by lock-free hash table and exclusive monitor, you can read our paper. Thank you.